So, yeah, working 5G silicon, no tricks up our sleeve. This is actually a live demo right now. So, on the bottom there, say again. Oh, you want to put your hand in and interrupt the millimeter wave beam? You can. It's all very low power.
Look at that.
How'd you get those antennas? That's on the base station side. So you guys see we've already started integrating the X50, the 5G modem into smartphone form factor, smartphone. Obviously, this is still too big, so we're going to continue to shrink it. We're going to continue to shrink it over the next few months. We actually have our reference designer ready, but we're not running it quite yet. And actually, if you come closer, you can see the millimeter wave antennas on the tip of on the upper tip there. I know.
I was actually hoping for some more rain.
Yeah. It's the green one. It's in the very far left corner. That's actually the millimeter wave antenna module that we have today, and we're going to shrink that further by another about 50% by the time we commercialize this in smartphones, so that we will be able to actually have multiple millimeter wave antenna modules in the phone, so that if your hand interrupts one, then data can flow through the
antenna gate.
Yeah. No, exactly.
Yeah. How many do you think you need? I don't
want that.
Probably 2 or 3. We're still experimenting.
So how did you guys go from 1.2 gigabits per second
to 5?
To 5.
Well,
4.5.
4.29. So what Anshul is referring to is that back when we announced that the X50 modem was working last October, we had only reached 1.25 gigabits per second at that point, and now we're up to 4.29 gigabits. It's the number of carriers. So back then it was only on 2 carriers, and now we're actually. This is 8 carrier aggregation. So 8 channels of 5G data coming to the modem, each one of them 100 megahertz wide. So this is 800 megahertz of bandwidth that the modem is absorbing and collecting data from, which is an insane amount of bandwidth. Right. But this is the promise of 5G, right? And the promise of millimeter wave. Yes, it's incredibly finicky. It's very difficult to get it to work, but the payoff is huge from a capacity perspective and from a user experience perspective. Now, obviously, you're not going to get the full 4.29 gigabits per second in the real world, because this is the total capacity of the cells when it's serving many users. However, we actually stand a chance of having data rates decidedly above 1 gigabits per second real world with this once it's deployed.
But this is fixed. What do you do mobile?
No, this is mobile. This is our mobile.
But
I'm saying right now,
these sort of cones that are helping you form beams, those are...
No, they're not forming beams. That's the base station.
Okay.
Yeah, so these are the base station antennas. So here, for the chamber, we're using these very directional antennas. But if you guys remember Durga's presentation, he showed what the base station and millimeter wave antennas are going to be like. They have 128 elements, a whole bunch of little squares, aligned in this matrix. That's what the actual, base station antennas are going to look like.
But when I was talking about mobile, I understand it's a mobile chip.
Yes.
But walking around is vastly different than standing still.
Absolutely. So
and that's what I was getting at.
So there's a couple things that we're doing to address the challenges of mobility with this, because it is extremely finicky, and there's been a ton of R&D over the past 3 years, 4 years on exactly how to get something like that working in a mobile environment. So there's a couple things. One is what's called beam forming that happens on the network side, and beam tracking on the device side. So the network is not going to transmit one ray of energy in one direction. It's actually going to transmit a whole bunch of them in all sorts of different directions. And they will travel into the real world. They will start bouncing off glass and buildings, off street lamps, off cars and trucks, and a whole bunch of them will arrive at the device. And then the device will do beam tracking. So it will start picking which one of these beams is providing the best signal and the highest quality and the fastest speeds. And it will do that dynamically, continuously, so that Sorry, go ahead.
I would say, just related, how will user speed affect that beam forming, beam tracking experience? Like like real mobility, as in walking, car, train, etc. How will that play?
Yeah, no, so it's definitely much more challenging, but we've already shown that working in vehicle mobility with millimeter wave already around our campus in New Jersey.
30, 40 miles per hour or 70, 80?
Up 70 miles per hour.
Okay.
And so it is in fact possible. It's for the Qualcomm pace car at Formula E.
Is there a bit of fall off performance though when you're doing 70 miles per hour versus just stationary?
Yes.
What kind of fall off?
I don't know what the fading is exactly, but it's part of the channel modeling that we're doing right now. But you have to remember that this is not being deployed in a vacuum, right? So this is being deployed as one layer on top of a 2 gigabit per second 4G layer. that is much less finicky, right,
Yeah.
than the millimeter wave stuff, right?